very to have the opportunity to speak today. I thank the organizers for holding this this conference online. So my topic today will be the Lorentz isometry group of closed Lorentz manifolds. So I just put the general setting. So the general question is which groups can appear at the isometry group of a closed Riemannian manifold. And we have general results that we can track back to Meyer-Senstein-Rode and then Kobayashi, Sternberg, etc., saying that this group is a Lie transformation group. So it's a Lie group, maybe not connected. And we can look at the situation of Riemannian manifold. So by theorem of Meyer-Senstein-Rode, we know that when the manifold is closed, this Lie group is a compact Lie group. So it's a old theorem, 39, I think. And much later, actually, the converse was if you take any compact, maybe not connected, then it can be realized as the full isometry group of some closed Riemannian manifold. So for in Riemannian settings, the situation is fully understood. And the next step is to deal with the case of Lorentz manifolds. So this is a more interesting case because you probably know that even when the manifold is closed, the isometry group may be non-compact. So there are more possibilities. And for instance, it may happen that the isometry group is infinite and discrete. This is a case that will be of interest for us. So before stating some theorems, I would like to explain two basic examples that you should keep in mind for the rest of the talk. So the first example is a nice three manifold, namely the Lie group SL2R endowed with what is called the killing metric. So you take the killing form on the Lie algebra, you push by left translation, and what you get is a bi-invariant Lorentz metric on this Lie group, which makes PSL2R as a model actually for the three-dimensional anti-de Sitter space. So now you take a co-compact lattice in PSL2R and you do the quotient on the right by this lattice gamma. You get a compact Lorentz manifold. And because the killing metric was invariant, you still have an isometric action of PSL2R on the left. And you can show quite easily that you obtain this way all the isometries up to finite index group. So basically, virtually, the isometry group is PSL2R. So this is a three-dimensional example that you can upgrade in higher dimension by making a product of your three-dimensional anti-de Sitter manifold with a compact Riemannian manifold. And you get this way isometry groups of the form PSL2R cross a compact Lie group, K. So that's the first class of examples we should keep in mind. And the second class is obtained this way. So you take a quadratic form of Lorentz signature on a Rn, and you see it as a flat Lorentzian metric. So then you do the quotient by translations. You get a flat Lorentz torus. What the isometry group of this torus? So it's just the isometries of your Minkowski space, which normalize the subgroup of translations, so Zn. So at the quotient, you get a semi-direct product OQZ by the n-dimensional torus. So OQZ is a set of matrices in OQ with integer coefficients. Okay. And if you moreover started with a rational form, Q, meaning that up to multiplication by a real, all coefficients are rational, then the group OQZ is actually a lattice in OQ. This is a theorem of Borel and Harish-Chandra. So in this case, you see that OQZ is big. It's a lattice basically in O1 n minus 1. And that's an interesting example because here you have an isometry group with a compact identity component, and the non-compactness comes from the discrete part, OQZ. From this example, you can even cook up other examples with a full discrete isometry group isomorphic to OQZ. Okay? So that's the second class of examples we should keep in mind. And I will now state a few classification results which were obtained the last 40 years. So the first one is a result by Robert Zimmer, which was very influential in the field. So you start with a closed Lorentz manifold, and you assume that a connected non-compact simple group G acts isometrically on M. Then G must be a finite cover of the group PSL2R. So it restricts a lot all the non-compact simple groups that could appear as subgroups of the isometry group. Then 10 years later, so for instance, first application of Zimmer's theorem, if you want to see, for instance, SL3R cannot act isometrically on a closed Lorentz manifold. 10 years later, Adam Stock and independently Zegib obtained a full classification theorem for the Lie algebra of the isometry group. Okay, so the manifold is still closed. And the Lie algebra has the following form. So it's a sum of three factors. The right-hand side factor K is either trivial or the Lie algebra of a compact semi-simple group. For instance, I don't know, O3. The factor A is an abelian algebra. That may be trivial too. And the factor S is either trivial or SL2R or some Heisenberg algebra or what is called a warped Heisenberg algebra. It means, so it's a class of extensions of the Heisenberg algebra by R, actually. But I won't detail this. What we have to retain is that the Lie algebra of the isometry group is fully understood, and the theorem is sharp in the sense that if you take a Lie algebra of this form, then you can build a closed Lorentz manifold such that the isometry group has this Lie algebra. Okay, so the result is sharp. And moreover, if you dwell a little bit in those papers, you find a pretty good description of the identity component of the group itself. Of course, the Lie algebra is not enough to understand fully the identity component, but we have a pretty good picture thanks to further analysis. Okay, so at the level of the identity components, things are really almost fully understood. And the next question is to understand the isometry group in the large, and especially the discrete part, iso-mg over the identity component. So it's a discrete group, maybe not finitely generated, actually, even when M is closed. I don't have examples where it is not finitely generated, but I don't have a proof that it is. So works of Zegib and Pichon have studied this situation in some intermediate case where you have a non-trivial identity component with a time-like orbit and an infinite discrete part. So this is interesting, but you still have an assumption about the identity component. In particular, you don't have any information if the group of isometries is discrete. For discrete groups, the only result I am aware of is a result of Zimmer. So using his called cocycle superrigidity, Zimmer proves that you can't have a discrete subgroup of the isometric group isomorphic to a higher rank lattice. For instance, you won't find SL3Z in the isometric group, at least as a discrete subgroup. Okay. And so this new situation dealing with discrete groups requires to leave the framework of Lie theory and to adopt the language of geometric group theory. That's why I will make a few recalls about the notion of growth of groups. So you start with a generated group, so gamma. So you have a symmetric generating set, S1, SR. Symmetric means that if S1 is in S, then S1 minus 1 is also in S. And for any element in your group, you define the length of this element as the minimal amount of words in your alphabet that you need to write your element gamma. Okay? And you have the convention that the length of the identity is 0. Now you can define an invariant metric on your group. So here it will be a right invariant with my notations. The distance between gamma 1 and gamma 2 is the length of gamma 1, gamma 2 minus 1. It's called the word metric on S. And you can also, in the more general setting of a compactly generated group, define a word metric in the same way. So instead of a finite generating set, you have a compact one. Why is this class of compactly generated groups relevant for us? Because this way you can deal at the same time with discrete and finitely generated groups, and also some kind of mixed group in the isometry group with an infinite but finitely generated discrete part and maybe a non-trivial identity component. So that's why we deal with compactly generated groups. But you can, for the talk, just consider the case of finitely generated. So let us define the growth of a group. You start with a compactly generated group, end up with a word metric. The group will be assumed to be locally compact. It will be the case for any closed subgroup of the isometric group of Lorentz manifold. And the growth of gamma is said to be polynomial if the volume of balls of radius r is controlled by a function of the form CR at the power d. So it's an asymptotic estimate. So the volume is relative to some right invariant R measure on your group. So if the group is finitely generated, it's just the cardinal of the ball. And an example of a group with polynomial growth is any finitely generated nilpotent groups. And of course, you have a celebrated result of Gramoff saying that virtually the converse is true. Another growth behavior is exponential growth, meaning that the volume of the balls is at least some exponential function of the radius for big radii. For instance, the examples you have to have in mind are the free group in two generators, for instance, the affine group of the line, or maybe every non-compact simple Lie group and every lattice in those non-compact simple Lie groups. Okay, so it doesn't exhaust the possibility behaviors. You have also groups with intermediate growth, but we won't really deal with that today. And I can now state the main theorem I would like to speak about today. So the theorem says you take a closed n+1 dimensional Lorentz manifold, so with dimension at least 3, because if not, my assumptions will be empty. And you assume that the isometry group contains a closed, compactly generated subgroup with exponential growth. Then you are exactly in one of the following cases. Either your isometry group is virtually a compact extension of PSL2R, or your isometry group is virtually a compact extension of what is called a Kleinian group, namely a discrete subgroup of the group O1D. And here D is controlled by the dimension of the manifold. So the dimension is n+1, and D must be at most n. Okay, so it's not difficult to check that in the first case, the isometry group actually has finitely many connected components, and the identity component is up to finite cover PSL2R cross a compact Lie group. And in the second case, it's not hard to check that the identity component is compact and the discrete part is isomorphic to a Kleinian group. One can deduce from the theorem under this assumption of exponential growth that every finitely generated discrete subgroup of the isometry group must be virtually a Kleinian group. Again, a Kleinian group is a discrete subgroup of O1D. So you have a huge literature about those groups. And even though I don't claim we know every Kleinian group, it's a very restrictive class of groups. Okay, so we understand quite a lot about those groups. So it's interesting to have this classification theorem. And we did not assume anything about the identity component of iso-MG. So the theorem in particular applies when the isometry group is discrete. So let's see some examples. You can deduce from the theorem, for instance, that the group F2 cross Z, so F2 is again the free group in two generators, or the group generated by two elements AB with this relation. So geometrically, you can think of the second group as a subgroup of affine transformations of the line generated by multiplication by 2, which will be A, and addition by 1, which will be B. Okay, it's a solvable group. So both groups have exponential growth, but they are not isomorphic to a Kleinian group. So it's interesting to notice that both groups can be embedded in O1D, but never in a discrete way. Okay, so those are not Kleinian groups, and you deduce from that and the theorem that they cannot appear as a discrete subgroup of the isometry group, and in particular, the isometry group cannot coincide with one of those groups. Another example is about isometric actions of lattices. So start again with n+1 dimensional Lorentz manifold closed, and assume that some discrete subgroup of the isometry group is isomorphic to a lattice in a non-compact simple Lie group G. So my next slide was about two examples of groups, so namely the group F2 cross Z. F2 is again the free group in two generators, or the group generated so that you can think about as a subgroup of affine transformations of the line. A is a multiplication by 2, and B is a translation by 1. Okay, so it's called the Baumschlag-Solitar group. And so what can we say about those groups? That they are not isomorphic to a Kleinian group. So it's not completely obvious. The point is that both groups can be embedded in O1D for D big enough, but never in a discrete way. So they are not Kleinian groups. They have exponential growth. So you can deduce from the theorem that they cannot appear as discrete subgroups of the isometry group, and in particular, the isometry group cannot coincide with one of those groups. Another example is about isometric actions of lattices. So we assume that the isometry group of a closed Lorentz manifold contains a discrete subgroup isomorphic to a lattice in a non-compact simple Lie group G. Then actually G must be isomorphic up to finite cover to O1D, with D controlled by the dimension of M. Okay. So you recognize Zimmer's result in the case of higher rank lattice. You recover actually Zimmer's results without using superrigidity theorem. And you also see that no lattice in SU1D can appear as a discrete subgroup of the isometry group, and this was not known until now. Let me also state a version of Tits alternative for the isometry group. So Tits alternative for the linear group says that a finitely generated subgroup of GL and R, let's say, either is virtually solvable or contains a free group in two generators. Okay, so here we can state the following result. So there is no assumption this time on the growth of the isometry group. It works for any iso MG. Okay, you take gamma, a discrete, finitely generated subgroup of iso MG. So discrete is important. Either this discrete group is virtually nilpotent and its growth degree is at most n-1. So we saw that nilpotent groups have a polynomial growth. So the growth degree is just the exponent, the optimal exponent you can put in the inequality. Or your discrete group contains a free subgroup in two generators. And in this case, you know that it must be virtually isomorphic to a discrete subgroup of O1D by the main theorem. Okay, so actually you can prove a Tits alternative with the usual statement, but it would require some generalizations of existing theorems by Romain Tessera. I will put the theorem later, and it's not done yet. So the main tool actually to prove those theorems is the notion of coarse embedding that I will describe now. So it is a notion that was introduced by Gramoff in his paper Rigid Transformation Group. It's a 1988 paper. And at the time, he called this placements and later on uniform embeddings. But now the usual terminology is coarse embedding. So before talking about coarse embedding, let me recall the notion of quasi-isometric embeddings. So you start with two metric spaces, X and Y, and a map between X and Y is called quasi-isometric, a quasi-isometric embedding, if you have the following double inequality. So the distance between the images of 2 points is controlled by two affine functions of the distance of the initial points. That's the point in quasi-isometric embeddings. Of course, the map is not continuous. It's very irregular, and that's why actually this notion is interesting. You require no regularity for the map. Okay, so the notion of coarse embedding is just a weakening of this condition. Instead of taking affine controls, upper control and lower control, you just take proper functions. Proper meaning functions that tends to infinity when the argument tends to infinity. So the definition is the following. A map between x and y is a coarse embedding. If you have an upper and a lower control, phi plus and phi minus, which are proper and such that the following double inequality is satisfied. So very roughly, a coarse embedding is a map which takes points which are close to closed points, roughly. And if some points are mapped to closed points, then they come from a pair of points which were already closed. So the important thing is that the control is uniform in the distance. So it seems to be quite a weak notion. Nevertheless, we will see what it is good for us when he's studying the isometry group of Lorentz manifold. So it comes from the following theorem of Gramoff. So in Gramoff, it's a remark actually, because the proof is a two-line proof. But the remark of Gramoff is that if Mg is a closed Lorentz manifold, then the isometry group iso-Mg coarsely embeds into the Lie group O1n. And because coarse geometry does not look compact objects, okay, does not detect compact objects, and because Hn is a compact quotient of O1n, it's the same thing to say that the isometry group coarsely embeds into the real hyperbolic space Hn. So we will explain in a few minutes why this is true. But let's just mention that our main theorem, the first one I quoted, is in some sense an upgrading of this coarse embedding into a nice Lie group homomorphism, which is moreover proper in the topological sense. The pre-image of compact sets are compact. And let me also mention what we mean by a coarse embedding between groups, such as iso-Mg and O1n. So a nice way to see things is the following condition. So for every pair Gk and Hk of sequences in the initial group G1, the sequence alpha Gk, alpha Hk minus 1 is bounded in G2 if and only if the sequence Gk, Hk minus 1 was bounded in G1. So you can check that for reasonable distances on G1 and G2, it satisfies the previous definition. And that's for groups, that's the definition we will retain. Before proving Gramoff's statement, let us just see, so let us mention that Gramoff's remark is very general in the sense that if Mg was a pseudo-Riemannian manifold of type PQ, then the same statements would hold with O1n replaced by OPQ. Okay, and it holds actually for every rigid geometric structure with a suitable group here. Instead of O1n. So the only particularity of Lorentzian geometry here is the group. It's that the group O1n occurs and the real hyperbolic space here occurs. So let's just see straightforward consequences of Gramoff's remark. So if a group gamma does not coarsely embed into Hn, then this group cannot appear as a closed subgroup of iso-Mg, at least when the dimension of the manifold is controlled by n+1. Okay. So that's a direct rephrasing of Gramoff's theorem. For instance, it can be shown that the group Zm does not coarsely embed into Hn when M is at least n. So for instance, you see that if M has dimension 3, you won't have Z2 in the isometry group as a discrete subgroup. If M is of dimension 4, you won't have Z3, etc. Another result states that no group with exponential growth and infinite center, for instance, the group F2 cross Z that we already met, can be coarse embedded into HD, whatever the value of D. Okay, that's a more involved result by Hume and Sisto, a quite recent one. And as a consequence, we recover the fact that we mentioned from our main theorem that F2 cross Z cannot be the isometry group of a compact Lorentz manifold of any dimension. Let me also quote an important theorem and very recent one by Romain Teixeira. It says that if gamma is finitely generated and amenable, then if gamma coarsely embeds into some hyperbolic space HD, gamma must be virtually nilpotent and the growth is at most D-1. So it's a very powerful theorem. I won't define what amenable means, but for instance, any group with sub-exponential growth is amenable. So Teixeira says that in this case, actually, the group is virtually nilpotent if it coarsely embeds into some hyperbolic space. Okay, so Teixeira's theorem is half of the Tits alternative theorem we mentioned. And it is a motivation to look now at subgroups of the isometry group which have exponential growth. Okay, because again, if they have sub-exponential growth, they will be amenable, and then we can apply Teixeira's result to them. So that's why in our main theorem, we are interested with isometry groups containing a subgroup with exponential growth. So I come back to Gramoff's statement, and we will check that actually the derivative cocycle is a coarse embedding. So we have our closed Lorentz manifold, and we chose a bounded field of orthogonal frames on this manifold. Of course, the field is not continuous, but just bounded in the bundle of frames. Now we fix some point in M, and we take some isometry of M, and the tangent map dxf can be read in the different frames, and it yields a matrix inside the group O1M this way. So you get a map dx from the isometry group of M to the group O1M. And the claim is that it is a coarse embedding. That's a remark of Gramoff. So what's the proof? Let's take two sequences, fk and gk, in the isometry group. Then by the chain rule, basically, you have that derivative at hx of fk hk minus 1 is the derivative at x of fk composed with the inverse of the derivative of hk at x. And you observe that if the right-hand side is bounded, so the right-hand side is bounded if and only if, of course, the left-hand side is bounded. And the left-hand side bounded means that fk hk minus 1 has a bounded one jet along the sequence hkx. And it's very classical in pseudo-Riemannian geometry that a sequence of isometries with a bounded one jet at along a converging sequence must be bounded in the isometry group. Okay, so thanks to the characterization of coarse embeddings for groups I mentioned before, we get that this derivative cocycle from iso mg to O1n is a coarse embedding. And then we can basically project a hyperbolic space, and we also get a coarse embedding of iso mg into the real hyperbolic space. So let me now speak about some invariants of coarse embeddings. So we actually Gramoff's insight was that the notion of coarse embedding is weak but strong enough to put constraints. Actually, not every space can be coarse embedded in any other space. So, and he found invariants. So the most basic one is growth. So you start with a compactly generated group with a word metric. And if you can coarsely embed gamma in a nice metric space, then the growth of the target space dominates the growth of gamma. It means that, for instance, if y has polynomial growth, then gamma cannot have exponential growth, for instance. So let me briefly explain why it holds. So assume that gamma has exponential growth, and let us check that the same must hold for y. So gamma has exponential growth means that a ball of radius r has basically up to constant exponential r elements, okay? And because alpha is coarse, it means that if you have pair of points in gamma sufficiently far away, let's say at distance at least 10, then the images are at distance at least, let's say 1, okay? So you start with a ball of radius r in gamma, and you take 10 net inside it. It means that you can find actually in this ball about exponential r points at mutual distance at least 10.
Charles, please.
Yep.
Yeah, it seems we have again the same problem.
Okay.
We are seeing just the statement of the lemma and not the proof that you are.
So I'm just the proof is not written. I just explain it.
Okay.
So we have this ball of radius r in gamma with exponential r about up to constants points which are at mutual distance at least 10. So now the point is that because our group is compactly generated, you can show that the upper control can be chosen affine. It means that your ball of radius r is mapped by alpha to a ball of radius, let's say 20 times r. And your exponential r points, which were at distance at least 10, are mapped to distinct points in this ball of radius 20 times r. It means that in a ball of radius 20 times r in y, you have about exponential, at least actually, exponential r points, and that's exactly to have the notion of exponential growth. So I roughly explained why if gamma has exponential growth, then y must also have exponential growth. Now let's go back to our situation of gamma, a subgroup of the isometry group, which is compactly generated of exponential growth, and try to apply the lemma to the coarse embedding given by the derivative cocycle. So there is a coarse embedding of gamma into the real hyperbolic space Hn. So at first sight, it does not say anything because gamma and Hn have exponential growth, so okay. it seems useless. But let us take the rough proof I gave, and let us remark that actually with the same proof, we can show that the image of a ball of radius n in gamma cannot be contained in a domain dn in y, the volume of which grows sub-exponentially with n. So if you suitably interpret this remark, you get the following corollary, that if gamma inside the isometry group has exponential growth, then it must have at each point exponential growth of derivatives. What does it mean? It means that at each point you have a constant, a positive constant a, and there exists a sequence in your group such that the derivatives grows exponentially with respect to the length of elements of the sequence. Okay? So why is it interesting? Because that's the first time you translate the intrinsic property of gamma, which is its exponential growth, into a property of the action of gamma on n. And that's, of course, interesting. So another geometric notion of interest with coarse embeddings into hyperbolic space is the notion of limit set. So let's take a general coarse embedding of gamma in the hyperbolic space. You can consider the closure of the image of gamma in the closed ball. So you take the closure, you see Hn as the open unit ball. Okay, so you take the closure in the closed unit ball. And the limit set is just the intersection of this closure with the boundary of a hyperbolic space. Okay. It's not hard to check that as soon as gamma is infinite, the limit set is non-empty. In the particular case of the coarse embedding given by the derivative cocycle, then we get a limit set at each point of the manifold, and we will denote this particular limit set lambda of x. And the point is that the limit set contains very important geometrical informations about the manifold. For instance, each u in the limit set at x corresponds to a totally geodesic like codimension 1 foliation on your manifold. So this is actually a rephrasing of a theorem of Abdelghani-Zeghib. And you see that if you have, for instance, an infinite limit set at x, then it provides a lot of totally geodesic like codimension 1 foliations. And it is known that in this case, the geometry of M is must be quite peculiar. There is still the problem of the regularity of those foliations. So those foliations are only transversally Lipschitz, which is a limitation to get directly geometric consequences of the existence of such a lot of foliations. Let me also mention the link between the limit set and local killing fields. Okay, so the limit set is again the one given by the derivative cocycle. Proposition: there is an open subset of the manifold called the regular set, such that if x is a point in the regular set, and if the limit set is infinite, then the isotropy algebra at x is big in the sense that it must contain a copy of the simple Lie algebra O1k. K is at least 2. Okay. The isotropy algebra at x is the Lie algebra of local killing fields vanishing at x. Okay. So the upshot is that when the limit set is big, you get a lot of infinitesimal symmetries locally. Of course, you know that generically there is no local killing field, so you guess that when the limit set is big, this abundance of killing fields makes the geometry very special. To produce those killing fields, we use the Gramoff theory of rigid transformation groups in a way that was actually formulated first by Nomisu in the 50s, and then Melnik, Pécastin, etc. So there is a machinery in some sense to produce killing fields. And the picture is that when the dynamics of the isometry group is complicated, then you must have a lot of killing fields locally on your manifold. Let me also mention the link between growth and limit set. I hope that I convinced you that if we show that the limit set is big, we will learn a lot about the geometry of our manifold. So actually, one very important step in our study is the following theorem. If the isometry group of a Lorentz manifold contains a closed, compactly generated subgroup of exponential growth, then the limit set is infinite at each point. So you have all those nice geometric objects, foliations, killing fields, etc., etc. So since I must conclude, I will just say that thanks to those geometric ingredients, we can produce actually a closed submanifold of M, which will be invariant by the isometry group, or at least by a finite index subgroup of the isometry group, providing by restriction a proper homomorphism from the isometry group to the isometry group of locally homogeneous manifold. So this way we are in some sense reduced to the locally homogeneous situation, which is better understood because we have a model space, etc. So we have more tools, partly algebraic, to understand the isometry group in the locally homogeneous case. That's why we can fully understand ISO-MG in this case.